So let us start, friend. So good afternoon, everyone, and
Good
I
afternoon.
hope that good afternoon, and I hope that all of you have a small amount of snacks before we started this lecture. So I consider that I assume that all of you are charged with some sort of snacks, right? So let us start. So in today's session, we are going to discuss the feature extraction using PCA. So before I start this principal component analysis algorithm, which is used to extract the features, let us first revise what we have seen in the yesterday's live session. So in yesterday's session, we have seen the feature selection and the feature extraction, these two processes as a part of dimensionality reduction. So both the process, their objective is to reduce the dimension of the original data set. But in what way they are different? So feature selection process, it aims to select the subset of features from the original set of feature, right? Whereas the feature extraction, the goal or the objective of feature extraction process is to map the higher dimensional data space or input space to a lower dimensional input instance space. So while mapping this higher dimensional input space or the data space to a lower dimensional data space, we want to ensure that there won't be any loss of information. So whatever information that we are carrying with the high dimensional input instance space, after reducing it to a lower dimensional, still we want to ensure that the information would be retained. Okay, some minimum loss of information is acceptable. Well, so as a part of the PCA, first we need to focus, or first we need to discuss on some of the important prerequisite for to understand the principal component analysis. So we'll see what is projection, what is mean, variance, and covariance, right? So it's better to take some example. So let's say that I want to take a picture of group of my friends who are standing like this. Okay. So my question is, so from which angle I should suppose to take the photo? So shall I take the photo from this angle, or from this angle? Okay. So that's my question. So shall we take the photo from this angle, or from this angle? Okay, so from my perspective, this angle is a better representation of all the objects that I'm going to capture using my camera, right? So I found that this entire faces, okay, all this group of, or the bunch of my friends who are standing in this direction. So principal component analysis is also used for the same purpose. We are using principal component analysis in order to minimize or to reduce the number of dimension of the original data set, so that this reduced dimension would better represent the entire information of the original dimensions of your data set. Okay, so that is what I just briefly mentioned in the beginning of this presentation. So let us say that we have this trained data set, and these are some trained data set point, and I just want to find out what would be the better projection in order to represent this point. So to find out the better projections for this data sets or for this data samples, let us say that I found that this could be one of the projection of this data set. So let us move these points to this projection, and let's see what happened. So all these data samples, we are ignoring the y coordinates, or the x coordinates values of these data points, and let us send them to this projection. So let's see how this looks like. So this looks like this. So we have transform, we have sent all these data points to this vertical line projection. And then we'll see, okay, would we have any other direction of projection? So let's say that we may also project this point in a horizontal direction, and that's what our next slide says. So again, we decided that why not to project this point onto a horizontal line. So we have decided this could be a horizontal projection line, best horizontal projection line that represents this data set. Okay. So we can ignore the vertical axis coordinates of this point, and we'll send or we'll transform all these points to this projection. Okay, so we send them to this projection. Now here, the question is that which line gives me the best projection of this trained data set or of this sample data set or this set of data points. So does this line gives me the better projection, or this line gives me the better projection? That is the next question. Can anybody please tell me, unmute your mic and please tell me which line gives me the better projection of this data points or this data set?
So line which is below.
Right. So you mean to say that, so this line gives the better projection of this data points. So exactly right. You are absolutely right. I think Sanket has given the answer, right? Or Chinmay?
Vedant.
Vedant. Good. Vedant. Good. Good. So this this horizontal line, this horizontal projection will give me the better projection or better representation of this point. Why? So I'll just make the I will just make the use of orthogonality principle, and I'll just make a single dimension of this vertical line and a horizontal line. And now we can better interpret this line that the points in this line, they are spreaded away. Okay, they are far apart from each other as compared to the line on the other side, that this left side line. So this is basically what we represent. The variance on the right side of the line is high as compared to the variance amongst the point on the left side of the line, right? So variance means what? How your points are distributed, how they are apart from each other, how they are spreaded into a input instance space, that is a space, simply a space. Okay, so that actually indicates the variance amongst your point or your data samples. Okay, so let us take one more example and we'll try to see how we are going to understand the principal component analysis. So in the beginning, we have mentioned that the principal component analysis, it is used to map the higher dimensional space to a lower dimensional space. So let's say that I have a housing data problem and I have given you the data set which consists of these 5 columns. That is, the first column says that the size of the house, and then second column is the number of rooms in the house, the third column is number of bathrooms, and third is the school around, and the fifth column indicates the what is the crime rate in the neighborhood of that location, house location. Okay, now I really want to transform. So because we have the 5 columns, that means we have the 5 dimensions for this data set. So I want to transform this, or I want to reduce this 5-dimensional input instance space to some reduced amount of input instance space. So can anybody tell me what would be the ideal reduction of this 5-dimensional input instance space? Can I reduce these columns to some 2 or 1 columns? Remember, while I am reducing this dimension, this 5-dimensional data set to some n dimension data set which is smaller than 5, I have to ensure that I do not lose the information. I cannot lose the information that this 5-dimensional data set carries. So can anybody tell me how we can reduce it to a lower dimension?
So if we want to reduce it, we might neglect the school around point and size point. maybe.
Okay, so you are actually touching to the answer, but somehow you have started thinking. Right. Great, great, Vedant.
Sir, we
Anyone
can
else?
uh,
Yes.
house data and surrounding information like that something.
House data and surrounding. Absolutely right. So anyone else? So you are moving to the answer actually. You are very close to the answer. Anyone else? Okay, so there are different ways that we can reduce this five-dimensional data to some n-dimensional data, which is we are considering this as value of n is less than 5. Okay, so let us see how we can reduce this five-dimensional data. So let's see that I have, from my perspective, I can separate these 5 columns into 3 and 2, and then transform these first 3 columns into a 1 column which says the size feature, and the remaining 2 columns, that is fourth and fifth column, have been transformed to a dimension which says that the location feature, because cool around and crime rate, these are basically the neighborhood. So I have better represented these 2 columns into a one column without losing any information. So location, is pertinent to the schools around, the crime rate, the shopping malls, the hospitals, and whatnot. Okay, and the size of feature, which actually better represents these first 3 columns, that is the size of the room, whether it is a big size house, the number of rooms, how many rooms are there in the house, and then number of bathrooms and so on, right? So I would better represent this first 3 column using a single column called as the size feature, and the remaining 2 column using the location feature. So that's how I have transformed this 5-dimensional input instance space to a 2-dimensional input instance space without losing any information, and that's what the PCA says. Now the question is that how do we achieve it? So let us represent this problem. Yes, of course, using a 2-dimensional Cartesian coordinate system. So the x-axis represents the number of rooms and the y-axis represents the size of the room. Now here I have considered only 2 dimensions instead of 5 dimensions. So now we have converted this earlier problem into a new problem, that we want to transform our 2-dimensional data into a 1 dimension. So we have represented the same problem using the 2-dimensional, and now we want to transform it to some 1-dimensional. And I mean to say that our observation have clearly, can be observed here. So we have mentioned during the discussion that a big size house may have a large number of rooms, and the small size house may have a very limited number of rooms, or we can say that only 1 or 2 rooms. So that's the reason why we have transformed this first 3 columns into a new column, that is the size feature. Well, now my problem is that I want to transform this 2-dimensional data into a 1-dimensional data. So I have to find out, somehow I have to find out the projection line that best fit this data points. Now remember here, we are not dealing with the linear regression problem where we are finding the best fit line that fits all the input instances on the space, right? This is not a linear regression problem. Here I want to find out a line, a projection line specifically, which actually transform this 2-dimensional data into a 1-dimensional data. So what would be the better position so that the projection will have the better representation using a 1 dimension? So let's see. So I'm drawing this line across this 2-dimensional Cartesian coordinate system, and I'm considering this as the projection line, which actually better represents my 2-dimensional data into a 1-dimensional data. So what I will do, after getting this projection line, I will move my data instances to this on the line, and just to make sure that we have transformed the 2-dimensional data into a 1-dimensional data, right? So using only size feature, we have started with the 2-dimensional data, that is number of rooms across the x-axis and the size of the room across the y-axis. We have transformed this 2-dimensional data into a 1-dimensional data where we have used only the size feature, one dimensions, to represent the data instances or the data samples. So let's see. So we have the two-dimensional size, two-dimensional data as the size of the room and the number of rooms. These are the dimension, and we have transformed this two-dimensional input instance space into a one-dimensional input instance space, which has only one feature, that is size. So that's what, my friend. These are the basics of projection. So what we have done is we are actually trying to find out the projection line, the best projection line that actually transform my input instance space into a reduced dimensional space. Okay, that means from two-dimensional to one-dimensional. And remember what we have made, the criteria that we have put or we have set is that we don't want to lose the information. The new lower dimensional input instance space should also better represent all the original dimensions of data set. Okay, so that's what. So let's go to the next one, that is mean, because I want to take it in a more dramatic way, that how this PCA will be used to extract the feature using some this prerequisite things like projections, mean and variance and covariance. Okay, so let's see what is mean. Let's say that I have this 3 points, this data set of 3 points, and I want to calculate or I want to balance this point. So what I will do is I have drawn the line. So this says that I want to balance this point. So to balance this point, one way that I would do is I will create a wall on the left side of these 3 points. Okay, so I have created this wall, and now what I will do is I will calculate the distance of these 3 points from this wall. Okay, so actually that gives me the mean of these 3 points, these 3 data instances. So the distance of first point from the wall is 1, then the distance of second point from the wall is 2, and you can say that the distance of this point from the wall is 6. So you can call it as this is 1, this is 2, 3, 4, 5 and 6, right? So I got the distances of all these points from the wall. Now I'm going to calculate the mean. How I would going to calculate the mean? So I will simply take the sum of all these distances. So 1 plus 2 plus 6 divided by how many points we have? We have 3 points. So the mean that I will get will be 9 divided by 3 is equal to 3. So somewhere along this point, I got the mean of this 3 point, which is represented in the next figure. So that's what I did. I have calculated the distance from first point, second point and third point, and then I took the sum of these distances and then divided by this total number of points. That gives me the mean. So here the mean is represented. Fine. So I hope you got the idea of how do we calculate the mean. Okay, so the distance of all the points divided by total number of points. Okay, so now how do I calculate the variance between these 3 points? Okay, if I really want to calculate the variance of variance between this 1 and 2 and this third point. Okay, so let's see what the variance is. Okay, so we have the 2 different sets of points. Let's say that this is one set of point and this is another set of point, and I just want to find out how these points, they are different from each other, how these points are spreaded apart from each other. So can I use the mean to just find out the spreadness or the distribution of this point? No, I cannot find out I cannot use the mean value in order to find out the spreadness or the distribution of these points from each other. Okay, I cannot use the mean. So what is left with me? I cannot use the mean of this. Why I cannot use the mean to find out the distribution or the spreadness of these two sets of data points? Because the mean of this set of points and the mean of this set of points are same. Because we have the mean same for both the data sets, So that's the reason I cannot use my mean in order to find out the variance. Otherwise, in the last lecture, if you in the yesterday's live session, if you remember, I have given you that data set of iris data set, and I told you that how do I calculate the mean. So I calculate the mean the way like the difference between each point and the mean, take a square difference of it, then take a sum of all the points divided by total number of points. So that will give me the variance. But in this case, I cannot use the mean approach to find out the variance. Why? Because I just observed that the mean of both the data sets, they are same, and that's the reason I cannot use it. So what is the alternative way? So what I will do is I will calculate the distance of each point from its center. So let's say that the distance of this point from the center would be 1. The distance of this point from the center would also be 1. But the distance of this point from the center is 0, because why? Because this point is itself a center. We have considered this point to be a center point, and we know that distance to that point itself is always 0. That's the reason its distance is 0. And the same way, the distance to this second data set points are on the left, it has 5, let's consider, and on the right it has 5, and the distance for the center point is 0 because that is center itself. Well, now we are going to calculate the variance. How we are going to calculate the variance? We are going to square up all the distances. We are going to take a sum of it divided by the total number of points. So what is the case here? So now, because this point is basically on the left side of the center, so usually its distance is considered as minus, and we know that we never measure the distance in a minus. Okay, the distances we have in the beginning lecture we have concluded that the distances are never negative, right? So that's the reason we are taking the square of all the distances. So if I take the square of all the distances, then I will have minus 1 square, then the distance of second point is 0 square, and the distance of third point is again 1 square divided by total number of points. So I get the answer 2 by 3. Okay, so 2 over 3 is the variance for this data set. The same way, I will also calculate the variance for this data set. So how do I calculate it? Again, I will take the distance of the first point from the center, so it will be 5 square, then the distance of the second point, which is actually center itself, so it will be 0 square, and then again the distance of the right side point, which will be 5 square divided by total number of points, that is 3. So the variance for this second data set, what I will get is 50 over 3 or 50 by 3. Okay, so that's how we are calculating the variance. So remember, whenever your data sets has same mean, or mean of your data sets are same, in that case, this is the second approach that we have adopted in order to find out the variance. So what is variance? That is how your points, how your data sets, your data samples, examples, they are distributed over the space. Okay, their variance, how they are apart from each other. Okay, their scatterness is basically the right word in order to define the variance. So how your data samples are scattered in an input instance space, to measure variance is used. So variance is the measure of the scatterness of your data samples across the input instance space. So that's what mentioned in the next slide. So take a square of all this. Why we have taken this positive? Why we have squared this distance? Because the distance on the left point is negative, and we know that the distances we never assume it as a negative, so we square it to make it positive, and that's the reason we have then took the square of each distances. So the variance for the first first set of data points is 2 by 3, and the variance for the second set of data points will be 50 by 3. Okay. So now this gives me the idea that how would I calculate the variance. So I will go back, and I left with this, that I want to calculate the variance of this problem. Actually, this problem I want to calculate the variance for these 3 points. So now I got how to calculate the variance for this 3 point. So what I will do is I will take the sum of all the distances, will then square it up, square each distance from the mean, and then we'll divide it by the total number of that points. Okay, so let me quickly take a pen and so that we can calculate it. So let's calculate the variance for this problem for these 3 data points. So variance for these 3 data points will be considered as, so the distance of this first point from the mean, because this is my mean, so the distance of this first point from the mean is 2, so 2 square, so that is minus 2 square, plus the distance of this second point from the mean will be 1 square, whereas the distance from this mean to this third point is actually 3. So I will take 3 square divided by 3. So it will give me the answer 4 plus 1 plus 9. So that is actually 14 by 3 is the variance for this 3 sets of point. Sorry, 3 point set. Is there any problem in understanding? Please give me a reminder.
No, sir.
So now the question is that how do we identify that in which direction our spread, our variance, or the scatterness of the data input points or the data samples are positioned? Okay, that is our next point of discussion. So let us do some operations on this sets of point. So let us move these points to ignore the vertical axis and move these points to the x-axis by using the x coordinate. In the same way, in the next iteration, move these points to the y-axis by ignoring the x coordinates, move it to the y-axis, and then you can now find out what is the best direction of variance. Okay, so here it clearly indicates me that the scatterness of the input instance space are better represented by this horizontal line, and we can say that yes, there are some amount of representation of this in all the points on the y-axis, but the variance or the spreadness or the distribution or the scatterness of this all the points that are represented on this horizontal axis, that is x-axis, is better than the y-axis. So when you project your points from this input instance space to this horizontal axis, then it is called as the variance of x. So when we are transforming this all the points to this horizontal axis, then we are ignoring its y coordinates value. We are just moving the points using only x coordinate value, and that's why it is called as the x variance. Okay, so horizontal line, it represents the x variance when we transform this point to the horizontal projection, and this is called as a y variance when we transform all these points to the vertical projections. So yes, we can say that this horizontal projection will give me the better representation, or we can interpret the in a better way the spreadness of the data samples. Well, now if this is the case, then I would take some other 2 sets of points. So these are the 2 sets of points that you can observe on this slide. So these are one set of point and this is other set of point. Okay, I'll just call it 2 and I will call it 1. Okay, now you can say that the distance of these two points from the
Excuse me,
center.
sir, only 10 minutes are remaining. Just 10 minutes are remaining to end the lecture.
Okay. I will just finish the variance and covariance, and then PCA in next lecture we'll see. Okay, good. So these 2 values are basically the x variance of this point. These are actually the x variance of these 2 points from the center. Let's go further. So this is basically the y projection of these 2 points from the center. And this is also the y projection or the y variance of these 3 points from the center. and this is called as the X variance. Okay, so now let us calculate this X variance. So we have just now seen how do we calculate the X variance. So if I want to calculate the X variance for these 3 points, then it would be calculated as minus 2 square, okay, plus 0 square plus 8. Okay, so this is my center actually. These are my center. So this is minus 2 and this is minus 2. So if I square it, I will get the 2 square plus 0 square plus 2 square. On the other hand, if I take the Y variance, then I will get 1 square plus 0 square plus 1 square, right? So this is basically minus 8 by 3 for this set of points, the X variance, and plus 8 by 3 for this set of points. So same way, the Y variance for this set of points will be minus 2 by 3, and for this set of points it will be plus 2 by 3. Okay, so that means the variance is not the different for both the set of point. But then are they really same? No. So there is a fundamental difference between these 2 points. So let us try to understand how these 2 sets of points, they are different from each other. Because if I calculate the variance, then I came to know that the variance of both the sets of points which are moving in this direction and this set of points they are moving in this direction, their variance is same. But fundamentally, looking at this figure, looking at this presentation, we can easily analyze that their directions are changed. They are fundamentally different from each other, even though their variance is same. So what we are going to do is next, we are going to use the covariance. So how do we then calculate the covariance, right? So what we are going to do is we are going to take the product of coordinates of each point, and then we'll take the sum of this product of coordinates, and then we'll check whether their variance is negative or positive, covariance is negative or positive. So let us take the first example, first set of points which are moving in the backward direction. So this set of points, so this point has minus 2 and 1 coordinate. This is 0, 0. This is 2, minus 1. This is minus 2, minus 1. And this point has the coordinates 2, 1. So now let us take the products of this coordinate. So when we take the product of the coordinates, then the product of this coordinate will be minus 2. The product of this coordinate will be minus 2. The product of this coordinate will be plus 2. And the product of this coordinate will be plus 2. So if you see properly, the points or the data points which are in this direction, they have the positive covariance, whereas the data in this direction, they have the negative covariance. And that is what our the next point of discussion, right? So although it doesn't matter whether it is a positive covariance or negative covariance, the point which is at the center will always have the 0 covariance. Remember, that is that does not change. So this point will have always a 0 covariance because it is in the center. So what we have done is, so let us represent this covariance using this. So the points which are actually used in this direction, they have negative covariance. The points which are represented in this direction, they have the positive covariance. So when the other words we can represent or we can define this relationship between the points as the points which are moving in this direction, they are negatively correlated, whereas the point which are moving in this direction, they are positively correlated. So positive covariance, or you can call it as the correlation. Sorry, this is not positive, this is negative actually. Let me take a eraser. Okay, so this is basically a negative covariance, or we can say that the negative correlation between the instances, and the points in this direction, they have positive covariance as well as they are positively correlated. Okay. Now, how we can say that? Now, if I take this example in this negative covariance, then in that case, as the size of the x-axis is increases, okay, as the x variance of these points are increases, the y variance of these points will be decreases. Okay, now this is not the case here. As the x variance is increases exponentially, or you can not exponentially, but at the same time the y variance will also increase. So there is increase in the y value. As the x value increases, the y value will also increases. So in this case, as the x value increases, the y value get reduced. It will get decrease. So that is the covariance. So let us calculate it. So the covariance for this point is minus 2 square minus 2 plus 0 plus minus 2. So that is basically the minus 4 divided by 3. Covariance for this is 2 plus 0 plus 2. That will be 4 divided by 3. Okay, so we are just actually taking the products of coordinates. So the product of this coordinate is minus 2 and this is again minus 2. Take a sum of it, minus 4 divided by 3. Same procedure is repeated here. So the covariance for this points is 4 by 3. It is positive covariance, and the covariance for this points, this set of points, is negative, that is minus 4 by 3, and that's why it is called as positively correlated or the negatively correlated. So now let's take another, let's have a look on the another set of points. Now we have this set of points and now we try to find out the covariance for these points. Okay, this set of points. So there are total 9 points. So the product of this first point will be minus 2. So minus 2 into 1, that gives me minus 2 times 1 will give me the minus 2. So 0 into 1 will give me 0. So 2 times 1 will give me 2 plus minus 2 times 0 will give me 0, 0 into 0 will give me 0, 2 into 0 will give me 2. Then the product of this 2 will be minus 2 times minus 1 will give me 2 plus 0 plus minus 2 divided by the total number of 9, and you tell me. So what is this? So the covariance for this matrix will be 0. So it is 0 divided by 9, so that will be 0. So why the 0? Because the points, the points in the set, they are actually scattered. They have the high variance. They are spreaded. The scatterness between them, the distribution is center. Okay, it is centered actually. So whenever your points, your data set points have, they are placed in center, then they will have the 0 covariance, or maybe they have the small covariance. Whenever your data set points, when they are moving in this direction, okay, that is backward direction, backward diagonal direction, then it will have negative covariance. And whenever they are moving in the positive diagonal direction, then they will have the positive covariance. So that's all from covariance point. So let us see what is covariance matrix then. Let's say that we have these sets of points. Okay, so let us move these sets of points to the center. How do we move them to the center? So we'll take the average of all the x and y coordinates of all the points so that we can move them to the center. So we have just moved the all the points to the center of this two-dimensional input instance space, and then we supposed to calculate the covariance matrix for this. So how do I calculate the covariance matrix? So covariance matrix, let's say that the first the top left field of this 2 by 2 covariance matrix, because we are using the two-dimensional input instance space, so my covariance matrix will be 2 by 2. So the variance of the top left field of this covariance matrix will be the variance of x. The bottom right time up. Okay, so I'll just finish in 2 minutes and then I will stop. I'll just explain you covariance matrix, because from next slide onwards the PCA starts, and I will take make the forum open for the questions, right? So just give me a moment, 2 minutes only. So variance, this right bottom field will be the value of variance of y, and this off the diagonal value, sorry, this off the diagonal value it will be a covariance for x and y. Okay, and this value will be same actually, and that's the reason it is called as the symmetric covariance. Why? Because of the diagonal value of this covariance matrix, they are same. Okay, so let us say that the variance of x axis is 9 that we have calculated. The covariance that we have selected is 4. Why? Because we have just seen the variance of x and y, and we realizes that both the variances they are having positive value. So let's have some covariance value 4, and we use this for of the diagonal field. So both this field, and then we have decided that the variance of y is 3. Why we have taken the variance of y is 3? Because we came to know that, you just recap or visualize that slide where I have shown you, when we map the data set points to the horizontal axis and the vertical axis, we have seen that the horizontal axis has the better representation as compared to the vertical axis. So that's the reason the variance of x-axis is we took larger than the variance of y-axis, and this is basically the covariance of x and y. This value is same, and that's the reason this is also called as symmetric covariance matrix. Okay, so now from this onwards, the PCA actually starts. And in PCA, as a part of PCA, what we are going to learn will be, we are going to see the linear transformation function, which actually transform one hyperplane into another hyperplane, or the points of one hyperplane into the another hyperplane. So the positions of the point will get changed. Okay, and that's the reason the we need a vector, okay, so as to stretch your hyperplane, right? So these two things we are going to learn: linear transformation function, which transform the function which transform the plane from one to other using eigenvector, and how eigenvectors are used, or how this new hyperplane will be drawn. So this new hyperplane will be drawn using or by calculating the eigenvalues of the eigenvector for the existing plane. So we calculate the eigenvalues for the eigenvectors of the existing plane, and then using that eigenvalues we transform one plane to another plane. Okay, so what do I mean when we are transforming one plane to another plane? That means I want to transform the points on the one input instance space to the points on the another input instance space. So point on the one input original input instance space means what? Our original dimension. And then we are transforming this original input instance space dimension to a new dimension, to a new input instance space which has lower dimension. So linear transformation actually transform your higher dimensional input instance space to a lower dimensional input instance space using the concept called as eigenvector and eigenvalues. So that's it from this slide. So thanks a lot. And if you have any doubts in this till what we have discussed, please ask me in the chat box, or you can unmute your mic. So what we have seen why we use the PCA. PCA we have used as a part of feature extraction. So to learn the PCA, we have seen some basics, okay, basic prerequisite for the PCA. So we have seen how do we get the projected line. Then we have seen how do we calculate the mean. Then we have seen how do we calculate the variance when we know the mean. Okay, and then if the mean of two data sets, if they are same, then how do we find out the variance between these two data set points that we have seen. And then we also discuss the covariance. Is there any problem? Tell me yes or no.
No, sir.
Okay, then my question is, I'll just put one question and then we'll stop. I mean, my question is, there is a spelling mistake in the question. How do I calculate the covariance? And how do I calculate the variance? If the means of both the data set points are same. Yes, be fast. We are running out of time. Product of x and y coordinates. Okay. So that's what. Is it covariance or variance? Covariance. Okay. So Bhumika is saying that the covariance is calculated as a product of x and y coordinates for each point, and then after that, that is the first step of calculating covariance. Then add them, okay, and divided by total number of instances. That is the total number of points. Okay, great. So that's how we can calculate the covariance. Now, I want to go back to Rishikesh, or Sanket, or Athang, or Akanksha. You can give me the the calculating the variance. How do we calculate the variance? Vedant, you are right. That is how we calculate the covariance. The product of x and y coordinates, and then taking the taking sub followed by dividing the total number of points. So sum, taking the sum followed by dividing the total number of points. Okay. So Atharva is saying that sum of square of all the points. Sum of square of all the points. So take a sum of square of all the points, and then so sum of square of all the points. So what? Which sum?
Divide by the number of points.
No, Sanket. That's not my question. You are right. Sum of square of all the points. But kya lene ka hai? Which value? How do we take that value?
Subtracting all the points from the mean and then squaring them and adding them divided by total number of points.
Exactly right. So we calculate the distance of every point from its mean, that is from the center, and then we square it, then add all the points in the same way, take a sum of all the points in the same way, that calculate their distances, square them up, and then add them, sum them, and divide it by total number of points. So that will give me the variance. So that's all. So if you have any doubt, nobody's asking me doubt. So what do I assume? So there are two possibilities. Either all of you understood, and second possibility is nobody understood. Yes, tell me. Any one question and then we'll stop. Don't you feel that this is, we are going good? Or please tell me if I'm going very fast, then I will try to make some changes in the way I deliver it. Give me your feedback in the chat box. What do you feel? And believe me, conducting the last lecture of the class itself is a challenging task for all the faculties. You just give me the feedback. If you do not understood anything, then I will cover it up in the next live session. No problem. So if you give me the feedback, thereby I can accordingly make the changes in the upcoming live sessions. See, ultimately everything is going up. So your understanding, your learning is more important than anything else. And particularly, I personally feel that if you lose the essence of the subjects like machine learning, then it would become very difficult for you, somewhere down the line when you are going for higher studies and all. Because in last couple of years, students, they do not pay the attention during the course time, and when they are going for masters abroad, then in abroad, majority of research is going on in data science, machine learning, data science using machine learning. So that's why my concern I have expressed is here. So I just conclude that nobody is having problem. So in the next live session, we'll take the linear transformation function, which transforms the all the points from the original dimension to a lower dimensional space, right? Using eigenvector and eigenvalue, and that is what the principal component analysis is all about. So thank you once again. Thanks a lot for patiently listening. You can mail me, you can call me at any time for any queries. Thanks a lot and have a great day ahead. Goodbye. See you in the next live session. And I would request all of you to subscribe to the channel to get the updated video. So today's live sessions video, I will upload it immediately after this session. Thank you.